Just let me know when to start.
Here we go.
Okay. Good day, all. My name is Albert AGBONKHESE, student number 373500. And today, along with me, my teammates SURAT and RUPESH we'll be presenting our project titled Electricity Demand Forecasting using Machine Learning. This project focuses on forecasting electricity demand in New South Wales, Australia, using models such as random forest, gradient boosting, and LSTM. The aim is to enhance short-term demand prediction using open data source from Kaggle, which support better energy demand and planning. Slide 2 now. So in slide 2, we discussed the problem definition. The main problem we address is the high fluctuation in electricity demand throughout the day and across different days of the week. These fluctuations make it difficult for energy providers to maintain grid stability and manage costs efficiently. Our focus was to design machine learning models that can accurately forecast short-term demand, reduce uncertainties, and support better operational decision-making. So in slide 3, we talked about the objectives. So our objectives had in this project, rather, we had 3 key objectives. The first objective was to forecast hourly and daily electricity demand for New South Wales. The second objective was to compare accuracy of multiple ML models, random forest, gradient boosting, and LSTM. Objective 3 was to identify time-based features that most influence electricity consumption patterns. These objectives help us structure our workflow from data collection to model evaluation. In slide 4, we talked about the dataset overview. The dataset overview we used was obtained for Kaggle titled Electricity Data from Australia. It includes 5-minute interval reading from the Australian energy market operators, specifically for New South Wales. Key attributes include dates, New South Wales demand, New South Wales price, Victoria demand, and then transfer. Our main target variable was New South Wales demand, presenting total electricity consumption in New South Wales, the value we aim to predict. So in slide 4, we have our data preparation. In the pre-processing stage, we handled missing values, converted the dates column into a date time format, and set it as the time index. We then engineered new features like hourly, day, weekday, weekend predictions, lag values, and then rolling averages, which helped our models learn both short-term and long-term demand trends. And finally, the data set was split into training, validation, and testing set to ensure reliable performance evaluation. And then in slide 6, so here we did the transition to EDA. So now let's move to the exploratory data analysis. Part of our project where we explore the underlying patterns in the data sets. Us the data was prepared, we performed exploratory data analysis to understand its structures and hidden trends. EDA helped us identify daily and weekly pattern, seasonal variations, and future relationships, which were critical for model design. As we can see in this graph, it shows the reconstructed New South Wales electricity demand over time. Each peak and dip represents one day's demand cycle. We can clearly see a repeating pattern. High usage during the day and low demand at night, confirming strong daily seasonality in the data. Now, I will hand over to SURAT, who will walk you through the exploratory data analysis and model approach sections. Thank you.
Thank you, Albert. Hello, everyone. My name is SURAT, student ID 376778. Let's continue from exploratory analysis of electricity demand, continue from alert. This graph illustrates the average 24-hour NSW demand profile. As we can see in the graph, the demand is lowest between 2 a.m. in the morning to 5 a.m. in the morning and gradually rises during the day and peaks between 6 p.m. and 9 p.m. due to the residential's energy use. This confirms strongly daily seasonality in electricity consumptions. And on this heat map, which shows average demand across weekdays and hours. Brighter area indicate higher demand periods, mostly during the morning and evening hours on weekends. In contrast, darker areas show low overnight uses and slightly reduced consumptions on weekends. This helps confirm both daily and weekend patterns in electricity demand for NSW. Furthermore, this graph we have which shows the daily demand amplitude, which measures the difference between maximum and minimum demand each day. The blue line represents daily fluctuations, while the orange line shows a smooth 3-day rolling mean. We observe that fluctuations are higher during the midweek, linked to business and industrial activities, and lower on weekend, indicating more stable usage patterns. So here our modeling approach. We begin with simple base models, including naive T-1 and seasonal naive to set a reference level of accuracy. Then we implemented random forests and gradient boosting as our main machine learning models. Finally, we apply LSTM, which is neural network for sequence data, a deep learning module suited for time series data. Our data set was split into 70% training, 55% validations, and 15% testing, ensuring fair and consistent model comparisons. Based on those model, we have a model evaluation matrix. These bar charts compare the model based on root mean square error, where lower value means better accuracy. The naive model has the highest RMSE, showing the weak performance. Meanwhile, gradient boosting, LSTM, and random forest achieve much lower root mean square error values around 0.08 to 0.09, providing that machine learning methods outperforms the baseline approach. And here come the summarized tables of our model result. We can see that gradient boosting achieves the lowest RM, SE, and MAE, followed closely by LSTM, while the naive model performed poorly. Overall, these results confirm that advanced ML and DL models provide the most accurate and reliable forecast for electricity demand in SW. Now I would like to invite our team member Rupesh Pon, who will be continuing the next part of our presentations, the model results, insight, and conclusions. Thank you.
Thank you, Surat. It's me, Rupesh Spoon, student ID S378248. Now I will be continuing the presentation with our model result, feature insight, and final conclusion. Let's move to the model result, actual versus predicted. The graph compares the actual energy demand with the predicted value from all the three models. All models, random forest, gradient boosting, and LSTM, closely follows the real and demand trend. Among them, gradient boosting stays the closest to the actual values and demonstrating the best performance overall. And the feature importance and insight. So here we identify which features had the strongest influence and demand. The most important one were our weekly lag 288 and rolling mean 72, which capture short-term and weekly cycle. This confirms that electricity demand follows clear time-based patterns. We also found that adding external features like weather or holiday could improve forecasting accuracy. Let's move to the feature importance and comparison. This slide compares feature importance between random forest and gradient boosting model. In both cases, rolling mean features, roll mean 72 and roll mean 24 dominate, showing that recent historical averages are crucial predictors. Lag features such as lag 1 and lag 24 also matter, indicating that past consumption strongly affects the future demand. So let's go to the business insight. From the business perspective, our findings provide several key takeaways. Predictable peak hour help utilities plan load distribution more effectively. Accurate forecasting reduces cost and minimizes the risk of blackout. The LSTM model is ideal for the real-time application, while the gradient boosting is faster and more reliable for operational decision making. Let's go to the slide 17, where you get the recommendations for future improvement. We recommend 4 steps. We deploy the LSTM model for day-ahead forecasting. We retrain our model monthly to adapt to seasonal shift, add weather and holiday data for multiple factor forecasting, and build an interactive dashboard using Streamit or Power BI to visualize and monitor prediction in real time. So let's move to conclusion. To conclude, our project successfully applied both machine learning and deep learning technique for forecasting electricity demand in New South Wales. Model like LSTM gradient boosting achieve high accuracy and strong predictive power. Our framework is scalable and can be adapted to other Australian states. Overall, the project helped us to strengthen our data analysis, modeling, and business interpretation skill, bridging technical insight with practical application. Thank you. That's it.
Amen.
Run off the record, brother.